Hello, hello everyone, and welcome to the Daily Space for Wednesday, August 29th of 2018. I'm your host, Dr. Andres Plazas, and as always, we're going to bring you a roundup of today's news from space and astronomy. So, for the first story of the day, I wanted to talk about the Higgs boson. So, as you all know, a few years ago, the Large Hadron Collider announced in 2012 that they had identified the Higgs field and in particular the Higgs boson, the excitation of the Higgs field. And this is a subatomic particle that is responsible for giving mass to for other fundamental subatomic particles. But today, physicists have announced another exciting announcement. Related to the Higgs field. They have made the first unambiguous observation, and unambiguous in the sense of particle physics, that it needs to have a certain level of significance in order to be accepted as an observation. They have made the first unambiguous observation of Higgs bosons decaying into a pair of bottom quarks. And this is surprising because actually the Higgs bosons, they decay most often in this way. This is the probability of a Higgs boson to decay in another in another pair of particles is the highest for the bottom quarks. So backing up a little bit, we remember that about in the 60s, scientists were looking for ways of unifying fundamental forces of nature. In particular, they found a theory that could unify the electromagnetism and the weak force, and then they called this the Electroweak Force. Um, However, this theory predicted that all particles of the Standard Model should have zero mass. So then people were a little bit puzzled, like, okay, what do we do? Because we know that particles do have mass. So a lot of group of scientists proposed a solution to this problem. They proposed the existence of a field that permeates the universe, and it is called the Higgs field. And then when the fundamental particles, subatomic particles, interact with this field, then they get their mass. Um, so this happened back in the 60s, and then, as many of you know, the final empirical evidence for for the existence of this Higgs field and the excitations of that field, which are called the Higgs bosons, we found evidence only until a few years ago, 2012. So, well, the way it works is like, how do we find these bottom quarks that they were finding today? So the Higgs bosons, they're made of, they're producing high energy collisions at the Large Hadron Collider. They're high energy collisions between pairs of particles that have been accelerated to nearly the speed of light. And because of this, these bosons, they actually don't have a very long lifetime. It's only about 10 to the minus 22 seconds, which is almost nothing. And it decays long before it travels a distance the size of an atom. So it is actually in practice impossible to directly observe the Higgs boson. So the way scientists do is that they observe the decay products of the Higgs boson, and then from those decay products they can infer the properties of the parent boson. So they found out that the Higgs boson have a mass of about 125 gigaelectron volts. It's happening in 2012. That's about 130 times the mass of a proton. And the calculations from the standard models, they predict that the Higgs boson should decay into pairs of different particles. In particular, it predicts that the boson should decay in a pair of bottom quarks with a 58% of probability, 58% of the time, almost 60%. It predicts that it should decay in another type of bosons, which are called the W boson and the Z boson, with 21% and 6% probability respectively. And then in other type of particles such as tau leptons and photons with 2.6% and 0% of probability respectively. And the interesting thing is that when physicists announced the discovery of the Higgs boson in 2012, they relied on its decay into the Z bosons and the W bosons and photons, which, as we just saw, didn't have as much probability as the bottom quarks. And the reason for this is actually simple. Those particular decays or decay channels, as they're known, are easier to identify. Why is that? Because at the collision energies available at the LHC, the Higgs bosons, they're only made in only one collision every 1 billion collisions. And so because of this vast number of collisions at the LHC that occurred, most of them occur through the interaction of the strong nuclear force, which is by far the strongest of the subatomic forces that are responsible for holding the nuclei together. And the problem is that when you have interactions that involve this strong force, the production of pairs of particles of matter and antimatter pairs of bottom quarks is actually really common. So basically, we just have a lot of background, and you have all these pairs of bottom quarks that are produced due to other processes, and then at the same time you have the signal from your Higgs boson decay. So it is very difficult to, almost impossible, to isolate these collisions with Higgs boson decay. So scientists actually had to use other techniques, and they had to use all different approaches, and in order to try to figure out how to identify this particular decay into the most probable channel. And the way they did it is that they looked at collisions in which the Higgs boson was produced at the same time as the W or a Z boson in a mechanism that is called associated production. So they look for the decay of the Higgs bosons into two pairs of bottom quarks, but at the same time they were looking for the decay of the W or the Z boson that gives us a signal that that's what was going on. And well, it is actually very, very important by itself to identify this new decay of the channel, because this channel of decay, because it provides confirmation for the standard model of particle physics as we understand it. But however, it's very important to gain a better understanding of this Higgs field, because when it was proposed back in the time, as I just told you, you could say that it was just an ad hoc theory that was added to the prevailing theory. So we had a problem about the lack of masses of all the fundamental particles, and then scientists just simply came up with this mechanism that just we found out that happened to work. Of course, it's not as simple as that. If you come up with an explanation, it has to make sense from the mathematical point of view. It has to make logical sense, and then of course, then you have to wait for experimental confirmation, which is what happened in the case of the Higgs boson. So, well, in order to understand better this Higgs boson, then people want to know if this Higgs field that was proposed is and the one that we're observing, they're actually the same. And one of the way of doing it is comparing the ratio of predicted to observed rates in the particular channel that they have discovered today. And they have found, if you take this ratio in a perfect world where the predicted and the observed fields are the same, then you would expect a ratio of 1. And this is actually what the collaborations at the LHC have found. So at the LHC, we have two main collaborations that they do some sort of friendly competition, but at the same time, it's good to have two different experiments to cross-check your results. So one of them is called the compact muon solenoid experiment, and the other one is called the Atlas experiment. And both of them measured that the ratio of the predicted to observed rates in this particular decay is very close to 1. Is one got 1.0 plus or minus 2%, and the other one 1.01 plus or minus, 20%. So still the error bars are a little bit large, but so far as the experiment is telling us, there is a consistency between the theory and the experiment. Then there's also other theories that say that there could be an interaction between the dark matter and the Higgs field, And this is another motivation of why we would like to better understand the properties of this Higgs field. So, well, in the future, the Large Hadron Collider is going to continue to operate through early December of this year, and then it will stop operations for about 2 years to get upgrades, and in the spring of 2021 it will resume operations with better capabilities. The accelerator and the detectors are expected to continue to take data through the mid 2030s and to record about 30 times more data than they have recorded so far. So we're looking forward to the discoveries that may come from all this large quantity of data. And then for the second story of the day, I wanted to talk about the New Horizons the New Horizons mission. And the New Horizons mission actually has reported that it has made the first detection of the target where it's going to do a flyby, the target in the Kuiper belt that is going to do this flyby. So this New Horizons spacecraft has made a detection of this target that is nicknamed Ultima Thule. And the cool thing is that it has made this detection more than 4 months ahead of the encounter of this object, which is planned to be in 2019. So, well, the missions teams, they're very happy for this because it means that the telescopic long-range reconnaissance imager was able to see this very small and dim object at a distance of about 100 million miles away, and was very hidden in this dense background of stars that you can see right now on your screen. And this is a very important for detection because the observations in New Horizons that is going to make in the next 4 months of this object, Ultima, is going to help the mission team refine the course of the spacecraft towards the closest approach to Ultima in 2018. And the cool thing is that the fact that they found this Ultima, that Ultima was where the mission scientists expected it to be, it actually indicates that the team has a very good idea of the orbit of this Kuiper belt object. So this is a very interesting thing because, well, the Kuiper belt object, as we know, is this sort of belt of objects that is beyond the orbit of Neptune. So in the solar system, of course, we have the inner solar system, the rocky bodies, then we have an asteroid belt, and then we have 2 gas giants and then 2 ice giants, and then beyond that, then we have the Kuiper belt object, and then we have the Oort cloud much further away. The Kuiper belt objects are actually very similar or analog, I should say, to the asteroid belt that you have between the inner system and the inner solar system and the gas and ice giants. It's just that they're more icy, of course. They're more like rocks, chunks of ice. And they're actually very interesting because you could say that they're the most pristine objects that you can think of, in the sense that they preserve the history of the early solar system. So when we study the objects in the Kuiper belt object, then there is a high chance that we're going to learn about the early stages of formation of the solar system. So this Ultima Thule object will be the first ever close-up exploration of a small Kuiper belt object and the farthest exploration of any planetary body in history. So yeah, and just to finish this story, then I wanted to know about the name of the object. So it's actually Latin for furthermost Thule, and this Thule place in medieval times, it was the place located furthest north, and it was mentioned in ancient Greek and Roman literature and cartography. So then the Wikipedia article also says that by the late Middle Ages and the early modern era, this Greco-Roman Thule was often identified with the real Iceland or Greenland or other places in northern latitudes. I just thought that that was interesting. Of course, this is just a nickname for the moment, and then eventually the International Astronomical Union will give it its official name. And then one more thing that I wanted to mention is that on my way here to work, on my commute, I was listening to a podcast by Michael Brown. Actually, it's a podcast hosted by Sean Carroll, a cosmologist at Caltech, and the podcast is called Mindscape. It's a new podcast, and then he interviewed Mike Brown, who is one of the scientists who has studied the Kuiper Belt the most, and in particular, he was very adamant for the reclassification of Pluto. And actually, his Twitter handle is Pluto Killer, and he wrote a book about why I killed Pluto and why had it come or something like that. And then also Mike Brown and one of his colleagues at Caltech, Konstantin Batygin, have been also proposing that or showing the world that there is evidence that points to the existence of another planet in our solar system. So I just thought it was curious. I was listening to this very interesting podcast, and maybe you all want to check it out. It was a very interesting podcast about a very interesting interview of Professor Mike Brown. And then to end the report of the day, the news of the day, we're going to talk about a new database that has been developed for stellar exoplanet exploration. This is a scientist from the Southwest Research Institute that wants to use big data to help the community to characterize exoplanets, in particular these alien worlds that are orbiting nearby stars. So this scientist, her name is Dr. Natalie Hinkle, and then in this press release they mentioned that, well, scientists, of course, they're focused on the temperatures of exoplanets. They're looking for exoplanets in the Goldilocks zone or the habitable zone. Then Dr. Hinkle actually points out that the definition of habitability is evolving beyond this liquid water and a cozy temperature. Planets also need building blocks for life, like hydrogen, carbon, nitrogen, oxygen, phosphorus, and then other rocky compositions, elements such as iron, silicon, magnesium, for a planet to be habitable. And then with the current technology, we can measure the composition of an exoplanet's surface and much less its interior, but we can measure the abundance of elements in a star through spectroscopy or spectroscopically, studying how light interacts with the elements in a star's upper layers, and we have talked about this a couple of times in the daily space in previous emissions. And then, using this data of spectroscopy, scientists can infer what a star's orbiting planets are made of at the same time, using the stellar composition as a proxy for the composition of the planets. So Dr. Hinkle actually made a database called the Hypatia catalog to help researchers explore thousands of stars as well as potential stars of exoplanet systems that they have been observed over the last 35 years. And this is the largest database of stars and their elements of populations within 500 light years of our sun. So Hypatia, or this catalog, has stellar chemical data of about 6,000 stars, which about 370 of them are known to host of planets. So so it is good that this type of data is available to the community, and then more important now that we're interested we're entering in an era of data-driven science. Dr. Hinkle and her colleagues want to work on a variety of machine learning algorithms to explore the ways in which the presence of a planet may influence the chemistry of the host star. And then, two final remarks that I wanted to make with respect to this news is that the name of the catalog, was named after the scientist Hypatia that lived in the late 300s or early 400s in Alexandria. Maybe I'm mispronouncing it. It's Hypatia, or well. Um, but she was one of the first women to have had this type of level scientific influence back in the time in the Hellenistic world. She even compiled the works of Ptolemy and Euclid, the Almagest and the Elements. And yeah, Dr. Hinkle mentions that Hypatia was one of her heroes, and that's why she wanted to name this catalog, this database after her. And the other remark that I wanted to do was the use of machine learning algorithms. Like some of you were watching the previous broadcast by Dr. Matthew Richardson, where he was showing about the craters of the moon, and here how at CosmoQuest we're trying to use citizen science to help improve the mapping of the moon and at the same time learn more about the history of the solar system. And one of the things that we're also working on here in CosmoQuest is using data from the public, from all the craters that when you go to cosmoquest.org, and then all those craters that you mark, we want to use those marks to train an algorithm, so the algorithm knows or learns from it, and then the algorithm will eventually automatically just to find the craters. So this is another application of machine learning, and this is another example of how these new techniques of machine learning and deep learning are getting used more and more in astronomy and in astronomy in general. And with that remark, I'm gonna look at the comments as usual, and thank you everyone for listening. And I'm gonna go back and say hi to everyone and see at your comments and see what questions do you have. Yeah, you have and what comments you have. So hello, Larry, Guido, Susie. Hello to the Nightbot, who's always there. My friend, the Nightbot. And hello, Hani. Hello, Ed. I'm Paranor. And hello, Ironheart. So Hani is asking, particles interact with the Higgs field and not the particles themselves. Yeah, the more a particle interacts with the Higgs field is the more massive that particle is going to be. So in the end, the way you express this is by terms of a differential equation that the field satisfied, and then you have a differential equation for each of the fields that are interacting, and then you have certain terms that couple, and then in the end, there are certain mechanisms in when you end up with a term that represents the mass of a particle that initially did not have any mass before interacting with the Higgs field. So what was the name of that podcast? The podcast that I was talking about is called Mindscape. It was recently released by Professor Sean Carroll from the California Institute of Technology, and he's a theoretical cosmology that has written a bunch of books about popular science books. But this particular podcast doesn't focus only on astronomy. He talks about other very interesting stuff like genetics. On the other day, he had the champion of poker player talking with her. But the podcast the most recent podcast, the guest was Professor Michael Brown. Pluto is still a world. Yes, it is. It just has a different classification. Will you get pictures of Ultima Thule of the same high quality as the ones New Horizons got of Pluto? That's a good question. I was wondering myself the same. I would think we should. On the other hand, I don't know if there are any technical limitations that will prevent us from getting the same quality that we got with Pluto. Pluto is already very far away, but now the thing is going even farther away. So unless there is some other technical limitation, you always have to think about the bandwidth and the download rate and who knows what else I'm not thinking about that could prevent us to have the same quality. But my naive answer would be that we should expect images like that. I might be wrong, so please check, but that's what I would think. Is there another theory that is awaiting confirmation from experiments at the LHC? Yes, there is. The main example of the most famous example is supersymmetry, which is a theory that says that every type of particle in the universe should have a partner that is called the supersymmetric partner. In order for some theories, for example, some string theories or other theories to work, then you need to have this existence of these supersymmetric particles. Like, for example, the electron should have a supersymmetric particle, or the neutrino should have like an S neutrino or a neutralino or something like that. And then the physicists were hoping that by now they should have found these extra particles or supersymmetric particles if they existed. The LHC has been running for a while, and people haven't found evidence for this so far. So now the supersymmetry is not completely ruled out, because theories can always come up with a different type of, like a flavor of the theory that could still lie beyond what the LHC is expected to see, or simply could be a different type of supersymmetry that could be seen when the LHC gets better data. But so far, people haven't found anything. So there were a lot of advocates for supersymmetry, but from the experimental point of view, so far they have been running out of arguments, because if we don't find anything, then that's it, you know. Is the LHC going to get more powerful or just most efficient with data in 2021? I think it's going to get more powerful. It's going to get upgrades. At the same time, scientists are always coming up with new ways of making the analysis techniques more efficient and the data collection techniques more efficient. And one of the examples that I remember a lot is the Tevatron at Fermilab outside of Chicago, that for many years it was the leader of particle physics in the world until the Large Hadron Collider came. But even at the end of the runs of the Tevatron at Fermilab, scientists were always constantly increasing the amount of collisions that they detected per second, or per unit area and per unit second, or what they call the luminosity. So for the Large Hadron Collider, the instrument is getting upgrades. I don't know the details of the actual upgrades, but at the same time, it wouldn't be surprising if scientists are coming up with more efficient ways of analyzing the data. Susie is a podcast junkie. Yeah, that's good. I also like to listen podcasts, especially in my commutes. And I might be doing. Actually, I will be doing my own podcast, but it's going to be in Spanish. This is one of the things that CosmoQuest and the Astronomical Society of the Pacific wants to support, and we've been working with Dr. Gay to make this happen. And hopefully, I will have in the future a podcast in Spanish. So, if you guys want to practice Spanish, there you go. Besides making the math work, what are the supersymmetric particles used in the universe? Um, I don't know. The use that I have so far is the two things that I always have in my mind when I think of supersymmetry, and I'm not a theorist, so it's very, very limited. The uses that I think in my mind. One of them is that the lightest supersymmetric particle could be a candidate of dark matter, the neutralino, if I'm not mistaken. I might be mistaken. I do know that one of the supersymmetric particles could be or is a candidate of dark matter. And the other one is to provide support to a string theory that I think assumes supersymmetry, if I'm not mistaken. All right, everyone. So if you don't have any more questions or comments, then I think we can call it for the day. And thank you, as usual. Thank you so much for watching. This has been the Daily Space, and as you know, it's a production of CosmoQuest created by the Astronomical Society of the Pacific. We would very much like it if you like us back. or even better if you support us by subscribing, or if you tell your friends on social media that this is CosmoQuest and we talk about cool things on Twitch. And we will see you all tomorrow. I think Dr. Gay will be back at 1 p.m. Eastern Time, 11 a.m. Pacific Time in the United States, and 7 p.m. London. And then on Friday, I will be back with all of you. So thank you so much, and have a good rest of the day. Bye bye, everyone.